Okay guys, let's look at a few of the circle geometry theorems. Okay, there are a lot of them. Okay, they're much easier to prove, except for this first one. The first one we're going to do is a little bit difficult. Or actually, let's start with some of the easier ones. Okay, we'll start with the following theorem. Okay, this theorem says that a line drawn from the center of a circle okay, so here's my circle. Oh, that's not a bad circle. Okay, so I'm going to draw a line from the center of the circle to the center of a chord. To the center of a, well, I've got two different spellings of center there, isn't it? Okay, let's stick with one. Center of a chord. Okay, now let's just quickly go through a few words that's going to be used. I should have started with that, I suppose. Okay, but if I have a circle, okay, that's not a nice circle, let's try again. Okay, if I have a circle, okay, also not nice, then any line that goes from one, or let's start with this, the circumference, the outside line, the actual circle is called the circumference. Okay, I'm sure you guys know that. The circumference. Okay, now if I connect any 2 points on the circumference, it's called a chord. That line is called a chord. Okay, now the chord divides the circumference into 2 arcs. Here's an arc here and there's an arc there, but the actual area of the circle, that little slice that I have there, that's called a segment. So an arc is the circumference of a segment. Does that make sense? Okay, here's another segment. So a chord also, it divides the circumference into arcs and the area of the circle into 2 segments. Okay, that's just some of the words that we're going to use. Okay, another word that we are going to use is if I take from the center of the circle to the circumference, that is called a radius. Okay, and then there's one special chord. Remember, chord is from the circumference to the circumference. A special chord that goes through the center. Okay, that one divides the circle into 2 semicircles. We call it half a circle. Okay, semicircle. And this chord that passes through the center is called the diameter. And you see the diameter is actually two radii. You see there's a radius this side and there's a radius on that side. So a diameter is just 2 radii together, so that we know the diameter would equal 2 times the radius. Okay, is there something else? Yes, there's one more thing. Okay, there's another line, and this line just, okay, mine doesn't, it just touches the circle. Okay, it means that it cuts the circle but only once. It's only one point, and that is called a tangent line. Okay, so if you have a ball that's on a surface, okay, like here, this looks like a ball rolling down a hill, the tangent line is the surface, and the tangent point is that point where that ball touches the surface. It's just one point. It doesn't cut through it like it would look if this ball was maybe lying in water. Then the water level would cut at 2 places. Okay, Good, so those are the words we are going to use. So if I say that a line is drawn from the center of the circle to the center of a chord, okay, a chord is now any line from one part of the circumference to another part, and I go to the center of the chord. That means that this length here is equal to that length there. Okay? So that's the conditions. The consequence of these two conditions is that the line will be perpendicular to the chord. Okay, and this one, we're going to look at the proof, is one of the easy proofs, and it's quite common, the way we're going to use this proof. Okay, so let's just see what are we to prove. Okay, so let's name our circle. We're going to say the center is O, and we'll call the chord AB. Okay, now with that in mind, who can tell me what is my to prove? What do I want to prove? Okay, let's, sorry, I have to say that as well. The point where this line, the midpoint of AB is M, okay? So that we're drawing a line from O to M, and we're saying that M is the midpoint, O is the midpoint of the circle, and according to this theorem, the line that we've drawn now is perpendicular to the chord. So what do we want to prove? Sorry, angle?
AM is equal to...
Okay, so you're saying angle AM, okay, but angle, if I write something like that, that's not an angle.
Oh, angle has to have 3.
Yes, so AM, where you go?
It's AMO.
Oh, so angle AMO.
It's equals to... Can I start with BM?
Yep.
BMO.
BMO, very good, excellent. Angle, we want to prove AMO is equal to BMO. And you remember that from the condition, another way of writing that same thing is that OM is perpendicular to AB. That's what we want to prove. But to prove it, exactly, beautiful. To prove this, I have to show that two angles on a straight line, these two angles are equal. That is the definition of perpendicular. Okay, so very well done. If you wrote that, you would have been 100% correct. Okay, now to prove it, we're going to need a construction. And the construction that we're going to do is we're going to draw the lines OA and OB. So construct OA and OB. Can you see why we did that? Why did we construct those two lines? What did we create?
Two triangles.
Beautiful, we have two triangles. So, what do you think our aim is going to be? Refer back to many of the proofs we did the last time. The idea was to find, to show. Now remember, we want to show that this angle and that angle is equal. Why would we have created two triangles to do that?
A common side.
Okay, no, I want to prove that triangle AMO is congruent to triangle BMO. Okay, congruent means they are exactly the same. They've got the same three sides. Now there's 4 ways to do it. Can you remember the 4 ways to show that something is congruent?
Side, side, side.
Okay, so we can either show side, 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 or
Side, 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 angle, side.
side, angle, side, or
side angle,
Excellent. Or
right,
good.
right angle,
Right angle, hypotenuse, and one RHS. Right angle, hypotenuse, and side. Which one can we use here? You should be able to immediately spot. Do I have three sides that's equal? Do I have a side and an interior angle and a side that's equal? Do I have a side and two angles equal? Or do I have a right angle triangle, hypotenuse, and a side?
right angle, hypotenuse, and side.
Why do you say we have a right angle?
We are proving that it's
Exactly.
perpendicular.
So we can't use it.
So we can use it.
No, that's our conclusion.
That's our aim.
That's our aim.
This angle, side angle side.
Which angle do you have?
Since we have what is this? A common side with two sides which are exactly the same.
Which sides are the same?
AM and BM.
AM and BM, yeah.
And then they share a common side which is OM.
OM, yeah, so we've got two sides.
I think it's side angle side.
You think it's side angle side. Okay, so we have this and that side. These two sides we have. This is a common side and those are equal sides, which means we have to have the inclusive angle, the angle in between those two sides. But that's the angle we're trying to prove is equal. Look, we're trying to prove that to be equal. So we can't use that. You can use... No, you can't. Okay. For time's sake, I'm going to continue. Okay. You were on the right track. Okay. And if you have started, you would have at least gotten some marks by saying, okay, we know that AM is equal to BM. Why? What's the reason?
It's given.
It was given. Beautiful. It's given in here. We are drawing it to the center of the chord. So M is the center. That means AM is equal to BM. Okay. So that was given. Okay. The second one, you said that OM is equal to OM. Why is OM equal to OM?
Common side.
It's a common side. It's the same thing. Okay. Now finally, there's one more side that are equal. Okay. Why is OA equal to OB?
Construction.
No, they were constructed, but we didn't construct them to be equal. Why is OA equal to OB? We didn't in our construction said anything of draw them equal to each other. We just drew them in. Okay, they are radii. Both are radii of the both are radii of the same circle. Do you see? It's a circle. The very definition of a circle is that all the points on the circle is the same distance from the center. So any two radii will be the same length. Make sense? Okay. So now we have, therefore, triangle AMO is congruent to triangle BMO. And the reason is we have three sides equal. And now we can therefore say, therefore, angle AMO is equal to angle BMO. You can write angle like this or with a little hat on the M. Okay, both is acceptable. Okay, and what is our reason? Why do we say those two angles are now equal? Why can we now say these two angles AMO is equal to BMO? Okay, guys, I'm a bit disappointed. Okay, from congruence. These two triangles we've just shown. Congruence means this means those two triangles are exactly the same. They've got the same angles. Okay, all of their angles correspond. Okay, so in other words, angle A is equal to angle B, angle O1 is equal to angle O2, angle M1 is equal to M2. Okay, everything, the OM is equal to OB, MB is equal to MA. From congruence means those two triangles are exactly the same, which means that this angle that we have here, because of the relationship between these two, they are congruent. So from congruence,